In this video, we're going to cover section 4.3 on area and definite integrals. So the objectives for this section are to learn how to find the area under the graph of a non-negative function over a given closed interval, similar to what we talked about in section 4.3, evaluate a definite integral, and solve applied problems involving definite integrals. So in this section, we're going to learn how to do this without needing to talk about Riemann sums. So you'll learn some shortcuts and some connections between antiderivatives and area. All right. To find the area under the graph of a non-negative continuous function, f, over the interval from a to b. Okay, step 1. Find any antiderivative, capital F, of our function f of x. So that when it says any, remember we always added the plus c, so you don't have to add a plus c, you can just choose the constant to be 0, so you can just find your antiderivative and ignore the plus c part. So the simplest one for which the constant of integration is 0. So in other words, just the antiderivative by itself. Then we're going to evaluate that antiderivative function using the values of b and a from our interval. B and a are the endpoints. Okay, and then compute, we're going to calculate the antiderivative value at b and compute the antiderivative value at a and subtract. The result, so the antiderivative of your function, plug in b, plug in a, and subtract, will be the value of the area under the graph. We'll have a different notation for this toward the end of this section, but this is just kind of walking you through the step-by-step process. All right, so our first example, find the area under the graph of y equals x squared plus 1 over the closed interval -1 to 2. Step 1, find any antiderivative of our function. So we're going to choose the simplest one. So this function's antiderivative, remember we would use our rules from section 4.1. We add a 1, so we get x to the third, divide by 3, plus constant of 1 means you're just going to get 1 times x. No need to put the plus c, so just the antiderivative. Okay, substitute our endpoints of our interval. Our interval was from -1 to 2, so we substitute in the endpoint, the right endpoint first, so plugging in a 2 and a -1. So capital F of 2 minus capital F of -1. Capital F referring to the antiderivative. So capital F of 2 was that x to the third over 3 plus x, so we get 2 to the third over 3 plus 2. And then we're going to subtract, right here, that's the subtraction, -1 to the third over 3 plus -1. And then we just clean that up. So that's 8 over 3 plus 2. This is -1. So I got the minus, and then still in the brackets here, this is -1 over 3 minus 1. If you distribute the negative sign, you get 8/3 plus 2 plus 1/3 plus 1. And then adding those together totals 6. So that would be the value of the area under the graph of our original function between the endpoints of -1 and 2. All right, so our quick check here, we're going to try this again. Refer to function 1, the function in example 1, the same one we just used, only this time we're going to calculate the area over different intervals. So part A, the area over the interval 0 to 5, and then part B, the area over the interval from -2 to 2. All right, so remember this was our function, and this was our antiderivative of it. So that would be our capital F. So for part A, we're going to do capital F of 5 minus capital F of 0. So if I plug a 5 into there, 5 cubed over 3 plus 5 minus, and then plugging in a 0, 0 cubed over 3 plus 0. So this is 125 over 3 plus 5. That's all a 0. So that's 46 2/3. Okay, over the interval -2 to 2. So plug in 2, then plug in -2 and subtract. So 2 cubed over 3 plus 2 minus, and then -2 cubed over 3 plus -2. So that's 4 2/3 minus, they've just added all this together, 8/3 plus 2 is 4 2/3 minus, and then all of this stuff adds up to be negative 4 2/3. So that becomes plus, and you end up getting 9 1/3. Once you get to here and have set this part up, you can just evaluate all that on your calculator if you want to. All right, so here is our other notation that basically is a better way to write what we just did in the last couple examples. So let f be any continuous function over the interval from a to b. Let capital F be any antiderivative of the function f. Then what we call the definite integral of f from a to b. So the definite integral, so the same symbol we saw back in 4.1 to represent an antiderivative, but if we're going to put limits on it this time from a to b of the function f of x with respect to x, is the antiderivative of the function evaluated with b plugged in minus the antiderivative evaluated with a plugged in. Exactly what we just did. Find the antiderivative, plug in b, plug in a, subtract. All right, so evaluate the integral from a to b of x squared dx. So our antiderivative would be x to the third over 3. So if I plug in b and plug in a, I get b to the third over 3 minus a to the third over 3. Okay, so that's it. It is convenient to use an intermediate notation, meaning a step in between. So we would write this as we're doing the problem so we don't, we can kind of keep it all together as one process. So we'll write down our antiderivative, and then outside of it we'll put b and a on the bottom and the top. Then we'll plug in b and plug in a. Okay, so that capital F is your antiderivative function. All right, so let's try each of the following. The integral from -1 to 4 x squared minus x dx. The integral from 0 to 3 of e to the x dx. And the integral from 1 to e of 1 plus 2x minus 1 over x dx, assuming x is greater than 0. All right, so part A. So this function, we want its antiderivative, which would be x to the third over 3 minus x squared over 2. Then outside of the brackets, the limit's -1 and 4. So then the top number is b. We plug that in first. 4 cubed over 3 minus 4 squared over 2 minus. Then we plug the bottom number in. -1 cubed over 3 minus -1 squared over 2. So this is 64 thirds minus 16 over 2 minus, this is -1/3 minus 1/2. So 64 thirds, this is 8 minus 8, distributing the negative, plus 1/3 plus 1/2, all adds up to 14 1/6. Okay. Part B, definite integral from 0 to 3, e to the x dx. So the antiderivative of e to the x is itself, e to the x, from 0 to 3. Then we plug in 3, so e to the third, minus, then we plug in 0, e to the 0. E to the 0, however, is 1. So we get e to the third minus 1, which using your calculator should approximate to be about 19.086. Okay, part C, definite integral from 1 to e, 1 plus 2x minus 1 over x dx. So again, our first step is our antiderivative. The antiderivative of 1 is x, plus this antiderivative would be x squared divided by the 2, but the 2 would cancel. So you just get x squared minus the antiderivative of 1 over x is the natural log of x. And then we've got our 1 and our e. So we first plug in e plus e squared minus natural log e, minus, then we plug in a 1. 1 plus 1 squared minus natural log of 1. So e plus e squared minus the natural log of e is 1, minus 1 plus 1, the natural log of 1 is 0. So that's e plus e squared minus 1. Distributing the negative gives me minus 1 minus 1. So that is e plus e squared minus 3. Decimal approximation using your calculator should be 7.107. So the procedure, find the antiderivative, plug in the top, plug in the bottom, subtract. All right, so this would be a good place to maybe pause the video, try these 3 examples, and then press play on the video to check your answers. All right, so A, the integral from 2 to 4 of 2x cubed minus 3x dx. Step 1, antiderivative would be x to the 4th divided by 4, so that 2/4 is where they're getting the 1/2. And then minus 3 would stay, x squared over 2. So minus 3/2 x squared. That's my antiderivative from 2 to 4. So we plug in a 4, 1/2, 4 to the 4th, minus 3/2, 4 to the 2nd. Minus, then we plug in a 2, 1/2, 2 to the 4th, minus 3/2, 2 to the 2nd. Make sure, because of this subtraction here, that every time the second expression is always in parentheses, the entire thing, because the simplifying will be wrong if it's not. All right, so cleaning that up, you get 128 minus 24 in that first group, minus, then you get 8 minus 6. So altogether, that totals 102. All right, part B. The integral from 0 to the natural log of 4 of 2 e to the x dx. So my antiderivative, the 2 would just stay there, it's a constant. The antiderivative of e to the x is itself. So that's my antiderivative function. Plug in the natural log of 4, so 2e to the power of natural log 4 minus 2e to the power 0. And you're going to simplify. So remember, the base of the natural log is e. And since the base of its power down here is also e, that'll just simplify to 4. So this becomes 2 times 4. E to the 0 is 1, so that's minus 2 times 1. So 8 minus 2 is 6. All right, part C. The integral from 1 to 5, x minus 1 divided by x dx. So this one we're going to have to split up first. This is one of those where you got to separate it. So x over x is 1 minus 1 over x. So the antiderivative of 1 is just x, minus the antiderivative of 1 over x is the natural log of x from 1 to 5. So if I plug in 5, we get 5 minus natural log of 5 minus 1 minus natural log of 1. Natural log of 1 is 0. So that's 5 minus natural log of 5 minus 1 minus 0. So the 5 minus the 1 is 4 minus natural log of 5, which approximates to about 2.39. All right, so what we call the fundamental theorem of integral calculus. If a function is continuous, f, and has an antiderivative capital F over the integral from a to b, then that procedure we just did, the definite integral from a to b, f of x dx is capital F of b minus capital F of a, that we've just spent this whole section learning how to do, is equivalent to doing the Riemann sum of the areas of the rectangles that we saw in the last section, f of x sub I delta x, the height of the rectangle times the width, but taking infinitely many rectangles. So taking the limit as the number of rectangles goes to infinity. The more rectangles, the better the approximation. So if you use n rectangles but take then the limit as n approaches infinity, you get the exact value of area under the curve. So that those numbers that we just calculated when we did this shortcut method right here, we'd use an antiderivative instead, represents the exact value of the area underneath those functions and above the x-axis. All right, So let's try this example 4. Suppose that y is the profit per mile traveled and x is the number of miles traveled in thousands. Find the area under y equals 1 over x over the interval from 1 to 4 and interpret the significance of this area. All right, this is just like what we just got finished doing. The function is 1 over x, so 1 over x dx from 1 to 4. So that 1 over x, I don't know why, I don't like, they write dx here, I'd rather see 1 over x and then the dx back here, but it means the same thing. So that 1 over x, the antiderivative is the natural log of x. Then you plug in 1, plug in 4, and subtract. So we get the natural log of 4 minus 0, which is about 1.3863. Okay, so the area under this function over the interval is this number. Here it said y was profit per mile and x is the number of miles traveled in thousands. So interpret the meaning. This is the graph. There's my function. X is number of miles traveled in thousands. Y is profit per mile. So this means that the area represents the total profit. So in thousands. So we multiplied our answer by 1,000, gives me $1,386.30. When miles traveled increased, remember it was between 1 and 4, x in 1,000, so mileage increased from 1,000 miles to 4,000 miles. So when the mileage increased from 1,000 to 4,000, right, this represents the total profit. Okay, example 5. Consider this function. Predict the sign of the integral by examining the graph and then evaluate. Okay, so we're going to graph y equals negative x cubed plus 3x minus 1. All right, so if you graph that function on your graphing calculator and look at it between the endpoints of negative 1 and 2. So if x were negative 1 and over here if x were 2. So notice between negative 1 and about right here, that whole function has values below the x-axis, meaning the area is going to be negative. Between right here and right here, the graph goes above the x-axis, that's positive. And then from about right here over to 2, we see it negative again. So it's pretty clear from this graph that there's more space below the x-axis than above it, right? Meaning, from the graph it appears there's considerably more area below the x-axis than above. Thus, we expect that the sign of the integral, when we're done evaluating, should be negative, right? Because there's more space that has a negative value. All right, so let's evaluate it. This was our function. So our antiderivative, the negative sign just stays. We get x to the 4th over 4 plus the 3 would stay. You get x squared over 2 minus, and then the antiderivative of 1 is just x from negative 1 to 2. So we plug in our 2. So negative 2 to the 4th over 4 plus 3 halves times 2 squared minus 2 minus, then we plug in negative 1. So the negative stayed, negative 1 to the 4th over 4 plus 3 halves, negative 1 squared minus negative 1. So we clean up as much as we can inside of there. Clean it up a little bit further. This one totals to a 0, and then this adds up with this negative in front to giving us negative 2 1/4, which would make sense, right? We said we thought the sign should be negative because there was more space below the x-axis than above when looking at the graph. All right, let's try another one. Northeast Airlines determines that the marginal profit resulting from the sale of X seats on a jet traveling from Atlanta to Kansas City in hundreds of dollars is given by P prime equals the square root of X minus 6. Remember, marginal profit is represented by the derivative of profit. Find the total profit when 60 seats are sold. So if we're given the marginal, the derivative, we're going back to finding profit, meaning we're going to have to work backwards and use an antiderivative. All right, so we're going to integrate to find our P of 60. All right, so the profit for the x value of 60 is going to be our definite integral from 0 to 60 of our marginal profit, right? We don't have a p function to plug 60 into, so we have to find it by doing this. All right, so our p prime was given. So remember, this is x to the 1/2. So our power rule means we add 1 to a half, giving us 3/2. Dividing by 3/2 is multiplying by 2/3. Minus antiderivative of 6 is 6x. Limits are 0 and 60. So we plug 60 in for all the x's here and gives me this. Minus, then I plug in 0. This is all just 0, so your calculator should give you a value here of negative 50.1613. So profit at 60 is a negative number. So that means when 60 seats are sold, Northeast profit is negative $5,016.13, meaning the airline will lose that amount of money on the flight. All right, so let's go back to that example. This time find total profit of Northeast Airlines when 140 seats are sold. Okay, so you can pause the video, try this one. It's the same function, same procedure, only instead of a 60, you're going to use 140. All right, so remember our marginal profit was given. So we integrate to find our p of 140. So this time it's the integral from 0 to 140 of our marginal profit function. Same antiderivative as before. This time though I'm going to plug in 140 instead of 60 and then plug in 0. Subtract. This time I get 264.3349. That's a positive number. So that means when 140 seats are sold, Northeast Airline makes, this was in hundreds, so multiplying that by 100 would give me $26,433.49. So whether you multiply by 100 or 1,000 or by nothing will depend on the units explained in the original problem. If it says it's in hundreds or in thousands, you have to pay attention to that. All right, example 7. The particle starts out from some origin. Its velocity in miles per hour is given by this function. So remember, velocity is the first derivative of position. So t is the number of hours since the particle left the origin. How far does the particle travel during the second, third, and fourth hours? So during the second hour is from starting off at t equals 1, right? So then your second hour is from 1 to 2. The third hour is from 2 to 3. The fourth hour is from 3 to 4. So you're going to go from 1 all the way to 4. All right, so remember that velocity or speed is the rate of change of distance with respect to time. In other words, velocity is the derivative of your distance function. And the distance function is the antiderivative of the velocity function. So to find total distance traveled between 1 and 4, we evaluate the integral, square root of t plus t, between the values of 1 and 4. So we integrate velocity between 1 and 4 to find position. All right, so we're going to write t to the 1/2 for the square root of t. Use our power rule, anti-differentiate, so add a 1 gives me 3/2, divide by 3/2 is multiply by 2/3. So this is a first power, so if I add a 1, I get a 2, divide by 2, evaluate from 1 to 4, so plug in a 4 first, so 2/3, 4 to the 3/2 plus 1/2, 4 squared, minus, then plug in a 1, 2/3, 1 to the 3/2 plus 1/2, 1 squared. Clean it up, 16/3. You can just type all this in your calculator as long as you don't forget your parentheses and your signs. But when you clean all that up, you should end up getting 73/6. Or 12 1/6 miles. All right, so summarizing section 4.3, the exact area bounded between the x-axis and the graph of a non-negative function is found by what we call the definite integral from a to b of some function by finding its antiderivative, plugging in b, plugging in a, and subtracting. If a function has area both below and above, the definite integral will give you net total area, or the difference between the sums of the areas above the x-axis and the areas below. So if there's more area above, it's going to be positive. If there's more area below, it's going to be negative. If there's equal amounts of area, it's going to come out to be 0. So this is what I just said. If there's more area above than below, it's positive. More area below than above, negative. And if the areas above and below are the same, the definite integral will be 0. All right, so that is the end of section 4.3.